We've just finished finding area between curves, and the basic principle there was we knew how to find area of a rectangle. So we looked at a rectangle that would span the shape that we were looking at, add up all the areas of the rectangle, let the number of rectangles go to infinity, and we got exact answers for our areas. And that was for shapes that were not polygonal. So we're going to do something similar for volumes. Let's start with some simple cylinders. But a mathematical cylinder is not the typical cylinder you probably visualize, with the base is circle or a tube-like shape. So now, mathematical cylinder. What's a mathematical cylinder? A mathematical cylinder is bounded by a closed plane region B1. We call it the base, and a congruent region B2 in a parallel plane. And the cylinder actually consists of all points on line segments that are perpendicular to the base and join B1 to B2. So let's take a look at some examples of mathematical cylinders. So you can have any base, a parallel base on top, connected with perpendicular lines forms a cylinder. So a typical cylinder that you probably are familiar with are the circular cylinder, rectangular box. How do we find volume then of these cylinders? Volume of the cylinder is area of base times height. So for the circular cylinder, area of the base, which is the circle, pi r squared, times the height. So circular cylinder volume is pi r squared h. Rectangular box, the bottom is a rectangle, length times width is its area, and then times the height will give you the volume of a rectangular box. So that leads us to definition of volume. So if you have a solid S that lies between x equals a and b, if the cross-sectional area of S is given by an integrable function, then basically we're going to have integral a to b, a of x dx represents its volume. It is very important that you remember that when we're using this formula, integral a to b, a of x dx, for the volume of a solid, that the a of x is the area of a moving cross-section obtained by slicing through x perpendicular to the x-axis. Well, what does that mean? So let's take a look at some examples. So let's take a look at volume of a sphere of radius r. So let's say volume of a sphere. So here's our sphere. If you look at cross sections perpendicular to the x-axis, they are cylindrical. And if you look at how, if you just take 1, 2, 3, 4, 5 cylinders versus 10 cylinders versus 20 cylinders, as the number of cylinders that make up the sphere go to infinity, you will get the exact volume of the sphere. So let's go ahead and see how to find volume of a sphere using our volume definition using integration. All right, so let's go ahead and see how to actually use what we have just defined as the volume. So let's label this coordinate on the sphere ax, y. So xy coordinates. X is the distance from the origin to here. Y is the vertical distance. And you can see then that this point A is on the circle of radius r. So we have equation of circle will be x squared plus y squared equals r squared. For volume of the cylinder, so we need to know how to find volume of the cylinder. Volume of the cylinder is going to be the area of the base, which is pi times radius squared. The radius for this particular cross section you can see is this vertical distance, which is the y. And so we can see area of that cross section is pi y squared. But we can use our relationship and we can see that y squared is r squared minus x squared. So the volume of our cylinder will be pi times y squared dx, or pi times r squared minus x squared dx. which means that now we can use our volume definition to get volume of the sphere as integral. So that will be integral negative r to r squared minus x squared dx. Or you can also say 2 times, because it's symmetric, 0 to r. So 2 pi 0 to r squared minus x squared dx. Pause the video here. Go ahead and execute the integration, and then we will check together what the volume formula for sphere is. Go ahead, execute the integration, please. All right. Assuming you have come back from pausing, you should have gotten 4/3 pi r cubed as your volume of sphere, which you probably already knew. Now you know why volume of a sphere is 4/3 pi r cubed. Some other kinds of solids are formed by revolving certain shapes about an axis. We'll start out with revolving a rectangle about the x-axis. This red axis is my x-axis. So let's see what happens if you take a rectangle and revolve it around the x-axis. Look what shape you will end up with. Can you see that? That's correct. It became a cylinder. You can see that from all directions. It's a cylinder, which means I can find its volume, pi r squared times the width, right? But how is this going to help us in finding volumes of solids of revolution? So that's what we're going to look at next. So let's take a simple curve, y equals sine x from 0 to pi, revolve that around the x-axis and see what happens. And you can see that it formed a solid. So a simple way to form solids is by revolving a curve, and we're revolving in this case with respect to the x-axis. That's our axis of rotation. And so how do we find its volume? So let's put a point on it and say x f of x. And let's bring a rectangle back. One end of the rectangle is on the axis of rotation. The rectangle is perpendicular to the axis of rotation. The other end is on the curve. If you take a rectangle perpendicular to the axis of rotation and revolve that, it forms a cylinder. And so let's revolve again and see what happens. As you revolve, you can see that red cylinder is part of our shape. And if you look at our shape from different angles, you can see or imagine this to be all these cylinders adding up to make our solid of revolution. So we want to know how to find its volume. What do you think we should do? Go ahead, pause the video here, see if you can come up with how to find volume of this cylinder. Go ahead. So similar to what we did with volume of a sphere, we're going to do the same exact process. Our function is y equals sine x, bounded between 0 to pi for x coordinates. Area of the base of the cylinder will be pi r squared times the height, which is dx. Substitute our y, which is sine x, so we have sine squared x. And then our integral would be integral 0 to pi area of the base of the cylinder times its height, and then finish the integration. We'll see we end up with 1/2 pi squared. So we just were able to find volume of solid of revolution, but remember we got that by looking at rectangles, revolving these rectangles perpendicular to the axis of rotation. That is very important to keep in mind. In this next example, look at this curve. I have f of x equals this polynomial function, and Let's put a coordinate on there and show a single cylinder which is gotten by revolving the rectangle like we did before. And let's look at all the cylinders from A to B, and you can see if the width of the cylinder is larger, you get less accuracy, but as the width of each of those cylinders goes to 0, you get an actual vase. So your job is to take any vase in your home and find its volume using solids of revolution. This next activity that we want you to play with, you're going to look, so here's a Toblerone candy bar. The dimensions are given to you. You are going to figure out what kind of solid is formed when you're looking at cross sections of triangles, equilateral triangles, what curves the bottom and curves and the top curve should be, so that it actually forms this candy bar, and then find its volume. So again, take a look. If my lower curve is 0.1 x squared minus 5, and top curve is sine x plus 10, when I move my triangle and the shape that I'm looking at, the bottom end is on the parabola, the top end is on the sine curve, and then whatever this height, the base of this triangle is, we equilateral triangle, perpendicular to the xy plane. Look at the shape that is formed, and you can find its volume by integrating from A to B, area of equilateral triangle, dx. And so that's how you find volumes of these. So that is the basis behind what we want you to do. There are 3 different kind of volumes you're going to find and create. Please follow the directions on the activity and finish the activity and write down your conclusions. In this next activity, you can put any top curve you want and bottom curve you want, and then find the volume. This top slider here will dictate whether you're going to write squares or semicircles or equilateral triangles or isosceles right triangles. You can clear traces and then move this slider to see what kind of shape is formed, and then find its volume. Same thing. So I'm going to clear traces before we use squares. Now let's see what shape you get if you use semicircles and isosceles triangles, and then explain how to find the volume and what it represents. So let's look at our sine x function again. Here's our typical rectangle. This coordinate is x, f of x. So this height here is f of x, this width is dx. Let's revolve around the y-axis and see what kind of shape it will form. You will see, here's the shape, and you can see the typical cylinder inside it, right? And so now you have to figure out how to find its volume. So let's see how to find volume using the cylindrical shell. So remember, when we rotated the rectangle across the y-axis, or parallel to axis of rotation, we got a hole in the middle of our cylinder. And so if you look at the volume, remember volume of cylinder, which was base pi r squared times height. So it's the outer cylinder minus the inner cylinder. Outer cylinder radius is r2, inner cylinder radius is r1. If you subtract, factor r2 square minus r1 square, r2 minus r1 is r dr. If you multiply by 2 and divide by 2, r2 plus r1 over 2, that is our average radius. And so our formula for volume is going to be 2 pi average radius, which is the distance of the rectangle from the axis of rotation, height of the rectangle, and then dr, or circumference times height times thickness. So let's see how that pertains to our example. So here's our sine curve. Here's our x f of x coordinate. We are going to look at the cylinders that were generated by rotating it around the y-axis. So our height of the cylinder will be this curve sine x. Our average radius, distance from axis of rotation to the rectangle, will become x, because our coordinate was x f of x. So integral 0 to pi, 2 pi x, that's the circumference, times the height, which is the sine x. When you integrate x sine x, remember using by parts you get that. You already know how to do that. So our integral will be 2 pi times all of that from 0 to pi, which gives us the volume to be 2 pi squared. So we will do more examples in the classroom, but these two methods, the disk method and cylindrical shell methods, is what we will concentrate on. So make sure you go through the activities that are in the handout.